Yeah, thank you very much, Victor, for the opportunity to give kind of a deep dive on quantum computing. And what I would like to share with you today is, since I don't know whether everyone is a quantum computing expert, I wanted to share some of the basics very quickly, and then give an overview about the quantum hardware and systems, and then also about various types of qubit implementations. And then in the main part, like focus on superconducting qubits. That's a technology which we pursue, and also which is from a technological perspective very far advanced. And then also our latest results and talk a bit about roadmap. So you, of course, all know bits and classical logic circuits, so I don't want to repeat that, but I want to kind of draw an analogy between the classical bit which we use and the classical logic circuit which is used in the classical semiconductor technology and classical computing. And in quantum computing, it looks right away a bit more complicated, as we are using the laws of quantum physics and build quantum bits, so-called qubits, and also quantum circuits. And the qubit can be represented as here by the so-called Bloch sphere, because we have a superposition of two states, the ground state and the first excited state. And this superposition is then represented by the Bloch sphere, and we can use kind of each state on the sphere for computation. So we have a much higher space for much more information which is stored in the qubit compared to a classical bit, which can only be 0 and 1. And the next, when you look at the quantum circuits, then this is a typical representation of such a quantum circuit where you have here one qubit, then here another qubit, and you then apply, as a function of time, you apply different gate operations to your qubit. And these kind of icons represent different gate operations. So the Adamar gate here, that indicates that it's a gate operation which only goes to one qubit. And if it's connected like this is a typical C0 gate, which then connects two qubits. And with the C0 gate, which is shown here, you actually create like an entangled state, which is also something which is very special, which you don't have in the classical computation, but you utilize this in the quantum computation. So these two analogy are simply the qubit and quantum circuit, similar to the classical computation. And you need also, similar to the classical computation, to build like a universal quantum computer, which is the goal. You need a universal set of quantum gates in order to build that. And what you directly see, of course, if you have n qubits, then they provide you with 2 to the power of n basis states. And when we look at the quantum physics we can use here for quantum computing, then we have these so-called superpowers of quantum mechanics, like interference of particles and waves. Also the superposition, which I just mentioned, the qubit uses, that you can be in multiple states at the same time, which we also call quantum parallelism. And you can utilize as a third phenomena entanglement, which means that you are in a correlated multipartite quantum state, and you can do this over a distance. And actually in 2022, the Nobel Prize has been given for the proof many years back of these of the entanglement. So I have another kind of an analogy also again. We have different bit states in a classical computer, and you operate on these n inputs, and of course you can operate simultaneously on these n inputs, and so the power of the classical compute doubles if you double the resources. And for quantum computing, that's very different, because you use the quantum bits. You prepare an initial state, the superposition of the two states, and you can create then all possible input data for compute in parallel and make use of the correlations and the entanglement. This means that a quantum computer can operate on the 2 to the power of n inputs simultaneously, which means that you have kind of an exponential increase of the power of your computation. And when you add an additional qubit to your number of qubits, then you theoretically actually double the power of quantum computation. And that's theoretical, so we are not yet, the quantum research and technology is not yet at that state, because there is still errors in those quantum computers on these qubits. And an error is unfortunately not as easy to correct as in classical. I will come to that later, and therefore it's a bit more complicated. One thing I would like to also quickly share is you can, of course, use classical computers to simulate quantum bits. And here is shown what number of resources you need in order to do that. So if you want to simulate a set of qubits, then you need a certain memory function for this. And let's start with 2 qubits, where you need 512 bits to simulate and represent an entangled state. If you go to 3 qubits, it doubles and so on. And you see very quickly that due to this exponential scaling, you come into a regime where you can no longer simulate quantum bits by a classical computer, because you wouldn't, it's just exponentially scales, and you cannot store the information anymore on the physical memory which you have in a feasible computer. And therefore, this we come right now, and you will see later, already in a regime where we compete with classical, or where quantum computers compete with classical computers. And what is also important, that you find also techniques for verification of the results. So why are we working at all on quantum computing? Because quantum computing may have this potential and provides us a new path to solve some of the hardest problems, in particular the ones, of course, where the resources which you need, the classical resources which you would need, exponentially scale with the parameters or with the complexity of the problem. So this is kind of an overview where, of course, easy problems can be easily calculated by computers, like multiplication. But if you look at factorization, at the reverse problem, then we all know that this is very, very hard to do, because a classical computer actually needs to go sequentially through all of the numbers, and the time for this is exponentially scaling. So therefore, this is one example, like factorization. There has been a quantum algorithm developed by Shor in 1994, which actually proved for the first time that quantum computers can be better than classical computers theoretically. So there are more problems which we look at to be used, where quantum computers can provide an advantage, in particular by simulating nature. These are problems where you have the quantum mechanics, which actually makes your problem exponentially increase in complexity. And the quantum computer uses the same physics as in nature. Therefore, physics, chemistry, material science, there are many examples where quantum computers provide an advantage. Mathematics and data with structure, like machine learning, ranking in the semantic groups, factorization. And there are also other problems, in particular, like optimization problems, sampling problems, risk analysis and option pricing, and these type of things, where also quantum computers can provide a speed up. But the speed up is different. We know from Shor's algorithm that there's proof that this could be an exponential speed up. This is also shown for quantum machine learning methods, but for example, for simulating nature, it can be greater than polynomial speed up, and for others like quantum Monte Carlo, for example, there's a quadratic speed up shown, but there's a lot of heuristics people are working on right now. So when we look at building quantum computing systems, because it's not only the qubit which we have to show and demonstrate, I mean, if you look back in history, then around 1980, Richard Feynman the first time showed the idea or presented the idea of a quantum computer, but at that time it was not clear how to build such a thing. And then it took quite a long time actually to also figure it out from the theorist how this works. A colleague of mine, David DiVincenzo, then published the 5 DiVincenzo criteria to tell the experimentalists how to build a qubit, and then all the different features and building blocks have been demonstrated over the last 20 years to really build a quantum computer. And this is a typical quantum computing lab. You see it looks like a true physics lab. You see here, I don't know whether you see my mouse, I hope. You see here the fridge. This is for cooling down the superconducting qubit chip in this case. You see lots of electronics in the back and lots of control, etc., etc. And over the last couple of years, we have actually moved the quantum computer out of this experimental physics lab and built a quantum system which is already put into computing data centers. And this requires a lot of systems development, and I will go in the next couple of slides a bit into detail in that you see what is worked on and what is needed. This is the IBM Quantum System 1, which we have built, and 8 years ago we have made actually the first quantum computer accessible through the cloud. And meanwhile, there are lots of users who work on advancing and accelerating quantum algorithms, quantum software, making it easier to program quantum computers, etc., etc. And of course, also the full stack is being built, what you see here. It starts from the qubits, which I mentioned before, but a single one isn't enough. You need to scale to a big number of qubits, therefore you have a quantum processor. You need the components and the wiring, the cryogenic platform. Control electronics is very important. And here you can ask, there are also new developments of going to cryo-CMOS, etc. The compiler, the error mitigation and error correction, the software and computing architecture, because a quantum computer is always connected to a classical computer, and also some of the algorithms which are currently developed are like a very connected between quantum and classical, where you go back and forth between a calculation on the quantum and the classical computer. You have the middleware, cloud, theory and algorithms and applications, etc., etc. So you see, in classical, I mean, if you look at the silicon technology, we continuously develop new things, but here it's really building something up from the scratch. Now I would like to share and go and explain a bit of the different types of quantum bits, because you've seen before that a qubit needs a ground state and an excited state. You need to be able to build a superposition, and you can imagine that there are a variety of different physical systems where you can build a qubit with. And some of them are shown here, and I will talk in a bit more detail about some of them. There are trapped ions, neutral atoms, and in these things you actually use the molecular levels in order to build your qubit. There is the superconducting circuits. Here you use the superconducting currents through a Josephson junction in order to build your ground state and excited state. Then you have photonic quantum computing, and you can also, of course, use spins or quantum dots. And in spins here, you use then the electron spin or the Hole spin to build your quantum dot or your qubit. There are other ideas of building solid-state qubits, like Andreev qubits or Majorana qubits. Majorana qubits have been very popular in the scientific community over the last couple of years because they theoretically have some topological protection, where you may go up to room temperature. But actually, this has not been really proven. There is not yet a true Majorana qubit developed. Then there are solid state defects like nitrogen vacancy centers in diamond, phosphor in silicon 28, dimers in silicon carbide. So you see there is a plethora of different physical systems you can use for building a qubit. And there is currently, of course, a lot of development in many of those different types of qubits. So here it's like a picture of an ion qubit from Sandia National Laboratory. It's an early picture. And the idea in ion qubits is you choose an ion, you cool these ions with a DC laser light, and then you control the qubit through laser pulses between the different states of the ion. And you can measure then by DC fluorescence and the CGD camera. You need multiple laser wavelengths. And with the, this one shows now, this picture here shows like a 3D silicon integration where you connect the segmented electrodes. Your ions are actually then captured in this line. So you see it's a linear arrangement, and you use electrodes to create like the and an RF quadrupole in order to create the electric field where you can trap the ion. And then you can move that around and also be able to shuttle the ions around. Here it's a follow-up from the ions. There are lots of companies also working on these ions, in particular startup companies. I mean, Quantinum is kind of came out of Honeywell in collaboration with another startup. IonQ, AQT, that's a startup in Austria. Electron, a startup in Germany. So you see there's lots of activity also in the startup community to build those things. And this is a sketch. This is from the IonQ webpage, where you see a typical arrangement of this integrated semiconductor ion trap. You have the laser, you have the control electronics, and also here lasers. The typical qubit error for these as published is 0.4%. Demonstrated so far have been about 36 qubits. And just to give you also a understanding of the coherence times, which is an important parameter for qubits, is 1 second. But the coherence times is not it's not enough if you want to judge the quality of a qubit, because you also need to take into account the fidelity of the gates as shown here, but also for the gate time. So how long does it take you to do a gate operation? And this is actually for ion qubits, unfortunately, a bit long. So they have long coherence times, but they also have long gate times, which reduce and also the potential for high speed operation. And one advantage is higher connectivity, but on the other hand, it's more difficult to scale these type of qubits. Quantinuum's latest chip is shown here. That's H2. It's a racetrack shaped trap, which you see here. So you can shuttle the ions around, and what you can achieve here is 32 fully connected qubits. If we move on, then neutral atom qubits, they have recently made quite some progress. They are pushed by several, or they have been pushed by several academic groups over the years. In particular, also Professor Mika Lukin from the Harvard University. And here you use, instead of an ion, you use a neutral atom. And this has in principle some disadvantages, because you cannot as easily trap it in an electric field. So what you do is actually you use like a laser to create an optical tweezer where you can trap your atom. And the other problem is that you have to make them also interact with each other. And in order to do that, you create actually a large Rydberg state, which is a larger atom. And then you can bring them close together in the range of about a few micrometers, and then you can create like also an entangled state by their interaction. here you see that's kind of a sketch which I took from the Quantum magazine. Actually, that's a very interesting article if you want to follow up on this. The advantage of neutral atoms is they also have long coherence time, but again, so far with the Rydberg blockade they have to use, they have also a very long gate time. There have been some recent ideas of how to reduce that, and that is, you know, people are working on to implement that. So a very active research field. The current state of the art is that there have been early this year arrays of several hundred trapped ruthenium atoms being demonstrated, and algorithms were run on 48 logical qubits, where each of them were made out of 7 or 8 physical atoms. And there was a startup which has been founded by a team originated from the Harvard University, and they are called QERA. And there's a recent publication also if you want to dive deeper into it. Then spin qubits, that comes now more closer to semiconductors, because for spin qubits, silicon or germanium is typically used. And here it's quite interesting because you can use the spin as an ideal two-level system. You don't have many more other states which you can excite. So therefore, spin has some interesting properties. You can leverage the semiconductor technology. It's small, so you can make very dense 2-qubit lattices. It's also fast in the gate times. You may be able to operate it hot, which means in this case hot means not at millikelvin but at Kelvin. And they also reach meanwhile good coherence times and quality factors. And this is based on the first proposal, which was done by 1997 by Daniel Loss and David DiVincenzo. And the major challenges which this field right now has is you need really very small devices. And because you need to come to one electron in your quantum dot or qubit, that you can create a qubit, which you then have to control, etc., etc. So you see here you create with electric leads, you create then traps, electric field traps for the single electron in a quantum dot. And to reach like a single electron and make this very reproducible, that you can control and tune these items is very, very difficult. So variability and reproducibility, reading out the signals, controlling the spins. Then to reduce the errors, you also need to go to isotope pure materials, for example, silicon-28. And tuning all these gates and the number of gates you need makes it also difficult to scale. But there are also people working on it. There are new concepts coming up, but I don't want to go in full detail. So in principle, what you do is, and this is a cross-section through such a device, you have in this case like a silicon substrate. You then have different leads. They are differently colored because they have different function. And you create like a quantum dot here, N1 and N2, and then you, with the gate here, you can then control their interaction, and you can do the gate operations and also 2-qubit gate operations. These are some examples for that people showed already, like 4-qubit and 16-qubit gates. What is happening right now is also that people move to germanium, because germanium shows faster progress gradient, I would say, in building qubits and scaling qubits. And just here, I would like to highlight also that last week there was a new publication by Intel on the silicon spin qubit technology. They built last year a chip which is called tunnel faults. It was demonstrated last June. And the chip is fabricated in a 300 millimeter line on silicon wafers, and also uses extreme UV. And the gate pitches are investigated from 50 to 100 nanometers. And the spin qubit devices are shown here. It's a SEM picture with differently colored the gates. The different gates are differently colored. So you have the yellow ones are the plunger gates. The blue ones are the barrier gates. You have then the green ones, which are the reservoir gates, and the red ones are the screening gates. So you see it's quite a complex setup for building, like here, 12 qubits. And there has been a recent publication, actually just last week, but obviously I seem not to have it here. I'm sorry about that, but there is a recent publication last week which actually did an elaborate characterization with a 300 millimeter low temperature prober at 1 Kelvin. Then photonic quantum computing is another topic. Here you have the idea is to use photons. There are two main approaches. They all use massive interferometer arrays, as are highlighted here. These are two key companies in that area, PsiQuantum and Xanadu. And there is one option is to generate large photonic cluster state. You do interfering of the three photon entangled states, but the challenges here are low loss propagation and components and a quasi-deterministic photon source. And the same is actually true also for Gaussian boson sampling. Again, also here, low loss propagation in the waveguides and all the components, and is very, very critical. So there's lots of work also on new materials and optimizing the stack of the photonic waveguides and photonic components, and also create the corresponding photon sources. And again, also here, I would like to highlight, because it's the field is to some extent a bit crazy. PsiQuantum is probably one of the startups who received so far the biggest amount of VC capital. And just last week, I think they raised 1 billion in Australia. And I think meanwhile, they have more than 2 billion of VC capital. Then I would like to concentrate on superconducting qubits, the hardware which we pursue. It has several advantages, which I will show you in a couple of moments. This is a chip, one of the early chips. It should indicate the different components which you need. One is a superconducting qubit, which is shown here. And in principle, it's a pretty simple device, because you have in a sandwich between a superconducting metal, an oxide, and a superconducting metal. Often what has been used is aluminium oxide, aluminium, and then you have shunt capacitances here in order to reduce the charge noise, and the junction is in the range of about 100 times 100 nanometer. So they are very easy to fabricate. Of course, the details are important. Then you have, as other components, a microwave quantum bus resonator in order to talk to the different qubits, and also have a microwave readout resonator, because you operate the superconducting qubit in the range of gigahertz. What you have, if you look at the electronic circuit, you have in principle a nonlinear inductor and a capacitance. This creates you the anharmonic energy spectrum which you need, that you have a separation between the zero and the excited states, the one state which is different to all the higher excited states, that you can control the excitation between the two. And the advantages is here the kind of simple device structure, the the decent lifetime which you can achieve up to the several milliseconds, and there is not yet a limit. So there has been improvement over the last couple of years over 6 orders of magnitude to increase the coherence time. And a very intrinsic advantage is that the gate time is very, very fast. And therefore you can build fast devices, and thus also a fast computer. And for the superconducting microwave resonators, you then have actually a this is used for the readout readout of the qubit states, and also as a noise filter, because you see you work between an energy distance of the 0 and 1 state of 240 millikelvin, so that's why you use a 5 gigahertz regime. And for the microwave resonators, it's just a harmonic spectrum. So if you go to the system level, then of course building such a quantum computer needs more than just the quantum processor and the qubit. So for the superconducting qubits, you need to work at around 10 to 15 millikelvin because of the energy levels, which I've just talked about. And you use a fridge. You have then the qubit control and the readout, which is managed through classical electronics at room temperature, or also moving to cryo temperature. You have analog microwave components and signal digitization. You need FPGA-based microwave pulse shape and control, microwave sources, etc. And what is important in the end, that you, of course, you also have a stable, low noise, and the cost is very important to take into account. And therefore, there is, as you can imagine, on all of these different components, the fridge, the electronics, the cabling, the microwave signal isolators, the cryogenic amplifiers, quantum processor, on all of these levels, there is active research and development to improve. In order to also measure the performance of a quantum computer, it's important that you understand how to measure it. And there also needs to be a metrics to be defined. And we are also working on the metrics, which we believe a good metric right now is not only one number, but it needs at least a number for scale, in order to scale the qubits, the quality, that you also have a high quality in your qubits and you can utilize the quantum physics, and the speed. And this is not only a qubit number, but it's really a system number. What you see here is actually that with increasing the number of qubits, you need to also move to a 3D packaging, because you can no longer wire all the qubits in one plane. Therefore, going to 3D and packaging is also a very important component. What you see here is some of the chips which we have developed and demonstrated over the last couple of years, from 2019 on, starting with 27 qubits. In 2022, we already demonstrated a processor with 433 qubits, and all of them needed, as you can imagine, different technological breakthroughs. And so there's, as you see, I don't go in detail into them, but working on how you can control and increase the yield of qubits and the performance, pump bonds, multiplexing readout, multi-level wiring, as I just mentioned before, and also flex I/O, as you will see in a minute, because it's getting also dense in the fridge. To show you a bit here how the qubits are laid out, what you see here on the right-hand side is how these 433 qubits in the Osprey chip are actually arranged with each other. And so there is a certain connectivity map for each of these processors, and we are using the heavy hex map because you can reduce again here also the errors and the crosstalk, etc. Just want to highlight that packaging, as I mentioned, is very important, because you need to, above 100 qubits, you can no longer do it in a plane to connect all the qubits. Therefore, you need to go to packaging. And here's a cross-section of such a package where you see the through substrate vias, bump bonds, the superconductor, and the qubit wafer, of course. And what is important to keep in mind, that this has to go to low temperature, to 10 millikelvin, and it needs to have also the microwave resonators, superconductors, etc. So there is also quite some development which is needed to make these things work. You can imagine that this is a picture of a cryostat where you have microwave cables going down, and it looks very nice. It's a very pretty picture, and I'm sure you have seen it before. But for scaling up number of qubits in the fridge is not very useful. So we have actually switched now to flex cables. You see here the miniaturization of this, and of course this is then making things denser and making things also less costly. The control electronics is another thing which is currently a lot of activity in scaling this further down. When you look at when we started with 5 qubits in 2016, you needed a full rack. When you have with 20 qubits, there was also a full rack needed. And then with generation 2 of electronics with 40 qubits, not a full rack. And now with 400 qubits, actually, we only need like a third of a rack. There is more going on because you need to continuously work on this and even go smaller. Therefore, there is also CMOS controller where you can further integrate all the electronics and bring this then even into the low temperature regime, not at millikelvin, but at the Kelvin regime. And this may also provide further advantages. So again, also this is an active field of research. So last year in December, we were able to demonstrate the first chip over 1,000 qubits. And again, pushing here scale and yield. And this means that for this chip, we actually used 5 superconducting metal levels and 2.5 times the qubit count in 1 times the space. So you see there is a lot of activity in really miniaturizing things, making it less costly and pushing the scale. And there, from this learning, there is, however, also a new processor which is called Heron, and the new the new addition here is that these are tunable couplers. And I don't want to go in full detail, but I will show you a chart in a few minutes where you see what the advantage is. And this tunable coupler provides you more quality, higher speed, and also helps with additional modularity. Because when you go and want to scale further out above 1,000 qubit, then you need to become modular. And this modularity you can achieve by then using different Herons or different of the quantum chips in parallel. There are also different couplers which connect them. But now here, what I wanted to show you is that the new Heron chip with the new tunable couplers actually has improved gate errors of 0.1, 0.3 to best 0.1. The crosstalk is almost 0, and you see again the gate time has been significantly advanced. This allows then further modularity, and I just indicated it. You want to connect chips in order to really increase fast the number of qubits, and therefore what we have demonstrated last year that chips can be classically connected, which means you can do a quantum computation on an individual chip, and you can then interact with each other also during the computation in order to allow and reduce the depths of circuits, or reduce the depths which certain algorithms need, and thus can do a more complex calculation. For this year, what we want to demonstrate is like different types of couplers, which are quantum couplers. This means these are microwave couplers between different qubit processors in order to make really good quantum computation on a larger chip, which is partitioned out of connected Herons. So this modularity is a very important parameter in order to scale further up. And this is also in the new system which we built. So this is a new IBM Quantum System 2, where you have here the fridge, you have the electronics on the side, and this is like a hexagonal layout, which you can expand more and more. So I don't know how I need to speed up, I think a bit, but I wanted to quickly show something on errors, because errors are important. They are still there. They are not yet corrected. And they can appear in different stages of your computation, whether it's at the initialization state of your qubit, at the gate operations, or also at the readout of your qubit. And a gate error is unfortunately not as easy to correct as in a classical system, because you cannot copy quantum information. That's based on the so-called no cloning theory, because if you read a qubit for copying, you actually destroy the information. So you need to utilize like parity checks in order to understand what the error is. And then you also have two errors, because you have bit flip errors and you have phase errors. In order to correct this, there is also active research on it, but so far, typically these algorithms of error correction have a large overhead. Therefore, error mitigation is a very appropriate tool to actually mitigate errors, which means you understand the error. You do not correct it, but you understand it, and you actually extrapolate to zero error. And there are different techniques which can be used. And in principle, I mean, simply spoken, in principle, you also have some overhead, because you have to do several measurements. You do some post-processing, and you can calculate the error out. And there are different approaches. One is probabilistic error cancellation, but let me explain perhaps zero noise extrapolation. What you do is you actually increase intentionally your error at different measurements, and then you can extrapolate to zero error. And this has been demonstrated, it has been scaled up to work on more than 100 of qubits. And this is actually a very nice tool in order to reduce the error. So now let me perhaps look at how do we come to quantum advantage, because today we are not in the quantum advantage phase where we can demonstrate that a quantum computer is better than a classical computer. And so if you look at this chart here, then you see the quantum circuit complexity as a function of the simulation cost. And let's assume you have a problem where the simulation cost of a classical computer based on a classical computer are exponential. With a quantum error correction, as I mentioned, you have a lot of overhead at the beginning. So that's not really useful at the beginning. But then if you use quantum error mitigation, you can actually live with a bit of more overhead, and you can come in a so-called sweet spot regime, where with quantum error mitigation, you can actually achieve an advantage compared to classical computing. And so this is where quantum, as I said, a quantum advantage may be. And what we have actually demonstrated last year is with a 127 qubit chip, which you, as mentioned before, you can no longer simulate this these 127 qubits classically. So you cannot classically define an exact result. You can do approximations, but these approximations actually for calculating did not work out. So we actually did a comparison between the Lawrence Livermore National Berkeley HPC and a quantum computer attacking a certain problem. And in this case, specific case, actually the quantum computer could calculate the right result. The approximations methods broke down, and we could demonstrate that the quantum computer still could calculate the specific experiment. So that has been published. I don't want to go in detail into it, but I wanted to mention that we are actually right now at this kind of cross section where a classical computer and a quantum computer are in competition for certain applications. And so it's a very exciting regime we are in. So there's also a lot of research on the error correction codes to reduce the overhead which is needed for correcting errors. And this is a paper which has been recently published by us, which demonstrated like a 14 times improvement over the normal surface code so far, which means that for 280 physical qubits, you can build like 12 logical qubits. So this requires, however, that we need a modular system, because we need to connect different qubit processors with each other. So we need these type of couplers. And that's actually currently happening. And I would like to show you now kind of a summary of the roadmap. And I show actually our roadmap because it's the most detailed roadmap you can find. We have in 2020, we're kind of brave enough to publish a roadmap, which is shown here, where you see at the bottom the hardware which is developed, and on the top you see the different software layers, and this contains the different abstractions of software. And of course here at this layer that's most closest to the hardware, that's the the tools which you need, the primitives which are developed for then the researchers who develop algorithms and want to compute this on hardware. And then on top you have like data scientists who do not need to fully understand a quantum computer, but they work then with the tools of the algorithm developers and solve their problems. So that's a bit the logic behind. You see the different years, and you also see the green check marks to demonstrate and to deliver what we have promised. So next year will be also, or this year will be another exciting year, because now we want to connect quantum processors with quantum buses. And we also have expanded actually the roadmap, which you see here, because we do a further look out into the future, into up to 2033, where we want to build systems with a large number of gate operations you can do. What's important is, as I mentioned, of course, the number of qubits, which is called in quantum terms the width of a quantum circuit, but also the depth of a quantum circuit, which means of how many gate operations you can do. And what you see here in this new roadmap, we actually increase the depth of this quantum operations. And just as a comparison for this utility paper, which I've mentioned before, the gate operations was about 2,800 or 2,900, and we increased this year up to 5,000, then going up to about 10,000, 15,000. And you see here in 2029 then a big jump, which goes up to 100 million. And this is actually then when error correction hits in. Up to then, we use error mitigation and then error correction, which then allows you to do, to kind of infinitely do quantum operations when you're able to correct it. And let me see. I think, yes, here you see how we scale up from the number of gate operations, the so-called depth. And I think with this, I need to stop. I would have a few things on connecting fridges. This is more on quantum transduction, which is another active field of research, but I think I will skip this because I already used a lot of time. Thank you very much.
Thank you very much, Heike. Very interesting, very comprehensive, and a lot of progress made. And we have several questions, but I would like to start. Before we start the discussion, I would like to ask if you can send us PDF of your presentation to post on Map2 website. It's possible? Okay, great. Thank you. So let me start the discussion, because I start from devices and after that we go to systems. So I think I already have an answer to my question, but I still ask. So I was wondered about this relation between qubits and equivalent classic bits needed to represent the qubits. And I wondered what was the rationale behind, for example, 2 qubits requires 512 bits. So while listening, I tried to think of it, and my rationale is that, okay, 512, it's 2 times 128, and 128 is 2 times 64, and 64 is double precision floating point representation of arbitrary number, and you need 2 numbers to represent it. One is amplitude, another is phase. Is it more or less so?
Yes.
Okay, yeah. Thank you for verifying this. My second question is about the 8-year history of operation of IBM quantum cloud system. So is there a statistics of workloads / use cases? So how it is used? So 8 years it is. You probably have good records of this.
Yeah, so actually there's a lot of activity. There are more than 400,000 users who program quantum computers. And also we have, I didn't want to brag, right? But there's a lot of activity. We have meanwhile a lot of computers online available. There are lots of quantum centers around the world which have access to our quantum computers. And these centers actually build also work on applications, right? I can give you one example. Fraunhofer, actually, they were the first to get a physical quantum computer. That was in 2021 already. And this is used completely by Fraunhofer to work with their partners. And as you all know, Fraunhofer is a research and development institution which works together with clients on use cases. And there are plenty of use cases people work on, whether this is on materials, whether this is on optimization. This is a car industry, airplane industry. There are new materials like batteries, like material suppliers, lots of industry which is interested in work together with us directly or also with other partners who have access to quantum computers. And meanwhile, and I may not, we have in Germany, there's a quantum computer. There is one in Rochester at RPI. There is one in Canada. There is one in Korea, in Japan. And there are many on the list to be delivered. There's really lots of activity.
Okay, thank you very much, Heike. I'll let other people ask questions. Sadas first and Kanat second.
Yes, so I had many questions. Maybe I'll follow up offline. I'll prioritize my question because of the time. Why is energy not a metric?
So energy is a metric. Actually, that's a good point what you asked. So if you look at the quantum advantage, then there are in principle different things. You can solve a problem which classically cannot solve, right? That's of course a big goal. Then you solve it with a quantum computer at less energy, you solve it faster, or you solve it with higher precision. All these things can provide a quantum advantage, and there may be different, there may be different possibilities for different problems. And energy right now, there is a lot of work coming up also in estimating better what the energy consumption will be, because if you do error mitigation, you may have also some classical computation. If you do error correction, you may also have some more classical computation. So that's something which I cannot give you a clear answer yet. That's really still part of the research, and it depends on the use case.
Yeah, the reason I asked was you had system level performance metrics and I didn't see energy there. That was the reason.
Yeah, because right now it's hard to identify. In the end, it's easy to measure, right? You solve a problem and you see how much it takes. If you look at the current one, which I showed in the this paper, there it was like a Sequoia with like 8 megawatt to like 36 kilowatt.
Yeah, but you also need to add the electronics.
Yes.
You need to compare the system level performance.
I think it is included, though. I mean, at least my impression it is total energy consumption. Okay, thank you, Sadas, Heike, and Kanat.
Thank you, Heike. Excellent presentation. My question is, you did not mention digital annealers. The D-Wave digital annealers have been around for 15, 20 years. They are not general purpose computers, but what do you see as the future of the digital annealing systems, quantum systems?
So obviously we focus on other systems. So I think we want to build like in the end like a universal fault tolerant quantum computer. And if you work on an annealer, you don't will not achieve it, right? And there is not yet a proof that you can do something with a quantum annealer better than a specific classical computer, right? If you would build a very specific classical computer to that problem, like an annealer is, there is not yet a proof that the quantum annealer is better.
Thank you.
Thank you. And David Gundlach, we're a little bit behind 11, but it's okay. It's very interesting topic. Go ahead.
That's fine. Can you hear me?
Yes.
Hi, Heike. Well, great to see you again. Wonderful presentation. I'm wondering if you could comment on specific differences between traditional semiconductor electronics, materials processing, and where the quantum industry needs to have that space shifted. You know, you talk about T1, T2. Do we need to think about how we characterize materials differently from what we've traditionally done around mobility or conductivity? Do we need to think about cryogenic electronics, that the PDKs that are available aren't useful at 4 Kelvin, and therefore there's a barrier to shifting foundries into being able to make circuitry at that level? What are the gaps in transitioning classical electronics industry and workforce into making it relevant for the different approaches used in quantum, I guess?
Thank you, David, for the very good question. If you look at cryoelectronics, right, what you mentioned, it's exactly right. If you want to design cryoelectronics at low temperature, then you also have to have the right PDK. You have to understand the characteristics that you can design the right things. That's currently going on. There's also increasing activity in that field. Then if you look at how to improve the different types of qubits, they have different challenges. And as you also said, sometimes what is important, for example, for a spin qubit, silicon spin qubit, germanium spin qubit, it's not so clear yet why, or it's not enough to do the characterization what you would do for a traditional transistor, because you are so sensitive to all these errors which may come in from different decoherence regimes or decoherence effects, right? And so understanding the decoherence effects and then also figuring out which material you need, what are these effects, they may be very different from the processing influenced, so it's really a new field or a new activity which is needed, and perhaps also new measurement instruments. That comes to your point, right? Probably also in order to understand the influence also of the different processing steps and the different designs. So that's definitely an open field where there is lots of stuff to do. And also when you look at the silicon spin qubits, for example, they are less mature. And there's a lot to be done in order to fully understand it. I mean, you see, for silicon, you need silicon 28 that you remove the decoherence which you get from the different isotopes, etc., etc. And also technology, right? I mean, being able to then do fast characterization at low temperature in order to identify and measure and get statistics is also an important regime.